Hi everyone. Today we are going to be talking about solving polynomial equations with different combinations of roots, both real and imaginary solutions. So if you guys look here at the do now, it says factor completely. The first thing I want you to do is try to factor this completely. And then after you do, see if you can solve for all the zeros. So pause it here and do that. Okay, guys, so I'm hoping that you did dots first because you noticed this was subtraction and this was specifically two terms that are perfect squares. So on the side, I'm hoping you did the square root of each term. And then I hope you realize you could have done dots again on this one because this was a minus sign. So your final answer should have three factors, 2x plus 3, 2x minus 3, and 4x squared plus 9. Now, as soon as it says solve, we have to set those same factor bubbles equal to 0. So when we solve, we're going to get two real roots, -3/2 and +3/2. But then over here, if you set this equal to 0 and you subtract 9, you're going to get 4x squared equals -9. And when you divide by 4, you're going to get x squared equals -9/4. When you take the square root of that, you're going to notice that you're going to get a negative square root. And I'm hoping you remember when we did imaginary numbers that the square root of a negative is imaginary. So we're going to get the square root of 9, which is 3, and the square root of 4, which is 2, I, because the square root of -1 is I. But we also have to remember that we can have a plus or a minus answer because we should have a total of, if you look back at the original question, 4 roots. So when we do this, we're going to have positive and negative 3/2i. Positive and negative 3/2i. Because the square root of 9 is 3, square root of 4 is 2, the square root of -1 is I. So we're going to have 2 roots come from that. So our final answer should have 4 total solutions because there's a 4 in the exponent, and that's called the degree. The degree of the polynomial equals 4 because that's the highest exponent. So this indicates that there will be the 4 total roots. There are 2 real and 2 imaginary roots. 2 real, 2 imaginary roots. Okay, so 4 total roots. Now, if you forget that plus minus, you're only going to have 3 roots, and that's not going to be appropriate because you should have 4 according to the degree. Now, if you look down below, it tells you to graph it, and it says all the roots are real. Is Sarah correct? When she graphed it, she said all the roots are real. So if you were to graph this, put this in y equals right now, and then zoom 6, and take a look and see what you see. You're going to see that it is going to indeed cross the x-axis in 2 real places at 1.5 and -1.5, which happen to be the 2 real roots that we solved above. Positive 1.5 or 3/2 and -1.5 or 3/2. And it's going to kind of look like a parabola like this. But something actually is happening down here. And basically, what happens is there's going to be 2 imaginary roots present, even though you can only see 2 real roots. So we have 2 real roots, but because we know that the highest exponent is 4, that means that there has to be 2 more imaginary roots kind of hiding out in the bottom here, not crossing the x-axis. So it says that she said all the roots are real, and that is incorrect. We have to answer the question, is she correct or not? We want to say no, she is incorrect because there are 2 real roots, but there are also 2 imaginary roots, since there should be 4 roots total. Okay? So now it turns out that actually all the roots are called complex. There are combinations of real roots and imaginary roots. There are 4 complex total roots, and they are made up of the 2 real roots and the 2 imaginary roots. The real roots you think are just 3/2 and -3/2. But actually, if you think back to the complex numbers unit, The complex numbers are of the form a plus or minus bi, where a is the real number and bi is the imaginary number. So this is really 3 over 2 plus 0i and 3 over 2 minus 0i. Those are your real numbers. And then the imaginary ones are going to be the ones that we solved above over here, 3 over 2i and negative 3 over 2i. So you think it's just 3 over 2i and negative 3 over 2i. But to make it complex, we actually just throw in a 0. 0 plus 3 over 2i, 0 minus 3 over 2i. So remember when we're working with a plus bi form or a plus or minus bi form, the a is the real number and the bi is the imaginary number. So there are 4 total roots, 4 complex total roots, 2 which are real and 2 which are imaginary. So summing up what I just said, the total number of zeros of a polynomial function is equal to the highest exponent that you see in the function. And that highest exponent is called the degree of the polynomial. The highest exponent is the degree. That tells me the total number of roots. So above it was 4. These zeros can be a combination of both real roots and imaginary roots. And those all are called complex solutions because they are comprised of both real and imaginary parts. Okay, now let's go on to example 2. It says consider the polynomial p of x. If you take a look, it says how many total solutions should there be? So if you look at the highest exponent here, you see that it's a 4. So there should be 4 total roots because the highest exponent is a 4. So now what are the roots or the solutions? So what we can do over here is factor. Remember, when we factor something that has x to the 4th, it's going to be broken down into x squared and x squared, whereas before it was x times x if it was just an x squared situation. So this is going to be an AM situation. So think about what multiplies to negative 4 and adds up to negative 3. Stop the video here and write it down. Okay, so I'm hoping you guys did x squared minus 4 and x squared plus 1 for your factors. And then I'm hoping you realize that x squared minus 4 can be broken down further into dots, x plus 2, x minus 2. So we have 3 factors. So now we're going to solve it out. We're going to get negative 2, positive 2, and those are going to be our roots. And then we also have this one. And when we solve this, we're going to have to subtract 1, and we get negative 1. And this is where we're going to see the imaginary roots come from. So we're going to get positive and negative I. So notice here we now have 4 total roots. We have 2 real roots, and they are negative 2 and positive 2. And we have 2 imaginary roots, and they are positive and negative I. So we should have 4 total roots, which is what we said in part A. So now go to y equals and type it in, and do it now. Y equals, type in the equation, and then press zoom 6, and then take a look at the graph, okay? Do it now. And you're going to see that it's going to look something like this. So it's going to cross at positive and negative 2. Then there's some kind of dip over here. It's not exact, but basically it's showing you that there's 2 real x-intercepts, indicating those are the 2 real roots. But then there's something going on down here, and that indicates that there's 2 more roots that are imagined. 4 total roots. So where it says describe, we're going to say there are 4 total complex solutions, but they are broken up into 2 real and 2 imaginary. Okay. And now it says how many x-intercepts does it have? There are 2 x-intercepts, and they were at x equals negative 2 and x equals positive 2. So the coordinates specifically are negative 2 comma 0 and 2 comma 0 if we're looking at coordinate pairs. Okay. That's it. Now let's look ahead to number 3. So now here's a multiple choice question. Obviously, I want you to do it algebraically as well as graphically if you can, but let's think about some common sense here. How many total roots should there be? If the highest exponent is a 3, which is called the degree, the highest exponent is a 3, there should be 3 total solutions. So if you look at the choices, which one is the only one that has 3 total solutions? I'm hoping you said choice 4. The rest of them only have 2, 1, or 2. So now let's actually graph it. So go to y equals right now and type this equation in and see what it looks like. Okay, now for those of you that graphed it, what you should see when you cross the x-axis is that it only crosses in one place at 2. Okay, and then it does something like this. It does a little dip like that. Okay, this is called a cubic function. And this is the only real x-intercept, x equals 2. Or this is the point 2 comma 0, okay? So that's why some people probably chose choice 2 because they saw 2 only, all right? But you know better. You know that there's 3 total solutions because the highest exponent is a 3. Now, if we had actually factored this, we would have used grouping. We would have grouped the first 2 terms together, done the GCF, and the second 2 terms and done the GCF. If we had done that, we would have gotten m squared, and then m minus 2, and then plus 4, m minus 2, common bubble, m minus 2, other factor, m squared plus 4. Setting this equal to 0, we will get the positive real root is going to be m equals 2. That's the one that I just said, crosses the x-axis there. And then when you solve this, yes, I'm still at the computer. You're going to get positive and negative 2i because the square root of a negative number. So you've got 3 total roots, 1 real and 2 imaginary, because the square root of the negative number is going to yield 2 imaginary. Again, don't forget that you need the plus and minus because it's very easy to just think that it's a plus. And then if you guys look back at the choices, you see this one here, that shows only 2 roots, okay? So that was a Regents question. It was multiple choice. Next one, take a look. It says, how many complex solutions does it have? And then find all the solutions, okay? So what you're going to do now is you're going to think about if you had multiplied out all the x's, how many total x's would there be? So remember, when we multiply, what do we do with our exponents? I'm hoping you say we add. So you have x squared, x squared, x squared, and 1x to the first, okay? So if you just take the highest x's from each factor bubble, you're going to have x squared, x squared, x squared, and x. So if you add 2 plus 2 plus 2 plus 1, you're going to have 2, 4, 6, 7. So it's going to be x to the 7th. So this means that there should be 7 total complex solutions, meaning both real and imaginary. 7 total solutions for your roots, okay? Now, are they real or are they imaginary? Well, we have to find them now. So you're going to take each factor bubble and you're going to set it equal to 0, okay? So I recommend you do the little tee it off thing here. And because this is already factored for you, it's a little easier because you can really just set each factor equal to 0, right? By teeing it off, okay? So set each one equal to 0 and solve right now for me. Okay, so here are my answers. I have negative 3 and positive 3. Those are real. I have positive and negative 6i. That's imaginary. I have positive and negative 1i. That's imaginary. Because when I did the square root of negative 1, right, I got I. And then I have 4 over 5. That's real. Okay? So if I count up the total real roots, it looks like I have 1, 2, 3 real roots. And I have 1, 2, 3, 4 imaginary roots. Remember, they have to add up to 7 total roots, and indeed they do because I have 3 real roots and 2 imaginary roots. 3 real, so I'm just putting an arrow here saying 3 real and 4 imaginary for a total of 7. Okay, this is the last one I'm going to do together with you, and then you guys are going to be on your own for the rest of the period to practice. It says example 5. This is actually a very recent Regents question, so let's start it because it does look a little harder, right? Which statement is true regarding a polynomial and its zeros, okay? So take a look at each one of these. Some of them look kind of scary, right? Let's start with the ones that are in factored form. Number 1 and number 3 are in factored form. So take a look first at this one, number 1, okay? If you were to set these bubbles equal to 0, you would have x squared minus 1 and x plus a, okay? If you set that equal to 0, you're going to factor this one, x plus 1, x minus 1, and x plus a, okay? When we tee this off, we're going to actually have 3 real solutions, negative 1, positive 1, and negative a. 3 real answers, because if you look at the exponents, this is going to be a 2 and a 1. This is a total of 3 real answers. So this says it has zeros 1 and negative a only. This is basically neglecting the fact that there was a 1 and a negative 1 here. So this one is out. Now, if we look at choice 3, we're going to have, when we set this equal to 0, we're going to get negative a, and we're going to get x squared equals negative 25. This is going to give me, when we square root, plus or minus 5i, okay? So I'm going to have answers negative a and plus or minus 5i for a total of 3 groups. So look at the answers. It says has zeros plus or minus 5 and negative a. So that's incorrect because it's not plus or minus 5, it's plus or minus 5i. So we cross that one out. So now look at choice 2 and 4 and read them over. Okay, do you see that both of those are not in factored form? So let's start with choice 2. We can factor this, okay? So I'm going to bring it over here. Choice 2. This was choice 1. This was choice 3. Here's choice 2. Can you do grouping? The answer is yes, you can. So we're going to get x squared, x minus a, plus 16, x minus a, common bubble, x minus a. Other one's going to be x squared plus 16. Now set that equal to 0 and see what you get for your roots. Stop it here. So for this one, I got x equals a and x equals positive and negative 4i. So if you look at this choice, this is incorrect. So this one's incorrect because it says x equals 4 and x equals a. So the final answer has to be choice 4. But I will say that this is also factorable. So if you factor this one now with grouping, just do it now and you're going to see that it is going to give you the right answer. All right, now you guys are on your own for the mixed practice. So go down below and do all these. They're all actually Regents questions. Just make sure you remember that you have to find all total solutions, both real and imaginary.